So I will spend first just a few minutes talk about some of the mega trends, and AI, and particularly in the technology spectrum, especially in terms of the new wave of digitalization and advance of the machine learning and the technology and algorithms, and obviously all the key breakthroughs and evolution on the architectural and the infrastructure. Then I will spend just probably 10 or 15 minutes talk about what I consider as the most exciting in the industry or application of AI. It's the autonomous driving and the cars that drive itself. And then if we have time, I will just spend a couple of minutes to talk about the newly created Institute for the AI Industry Research at Tsinghua University. In fact, this is something I've been trying to do for quite some time. All right, with that, let's just look at some of the things we have done in the last 30 years. If there's one thing in the IT industry I consider as the most significant, it is digitization. Back in the 80s, in the 90s, we start to digitize contents, and the music, the speech, the pictures, the video, and with that, we produce essentially everything today in terms of digital, your TV, all the photos you see on the internet, and also all the documents you see on computer, Excel, PowerPoint, Words, all those things are digital. And we consider those things, take this for granted, but it took a lot of efforts. In fact, I was one of some of the early people working on the video compression and the music compression and MPEG and H.26x. The second wave really started in the mid-90s, and we're trying to digitize enterprise, digitize your companies, the ERP, CRM, and the HR system. We try to digitize the supply chains and all the workflow, the BIs, and we invented database, and eventually led to all the cloud computing. So that was quite significant for the whole industry. And at the same time, consumer internet simply exploded because of the digitization and of course the TCP/IP. It started with POTOS, then was search, social, e-commerce. US, obviously, there was Google and Facebook and Amazon. In China, in parallel, there's Baidu and Tencent and Alibaba. There, of course, there's a sharing economy, there's a video and communications, like the Zoom we're talking about, using about today. And Netflix and iQIYI in China. And the later stage, and especially last few years, our currency, money, excuse me, becomes digital. And we using payment with our mobile phones that become really ubiquitous. And China actually took a leadership in this regard. In fact, China is probably the largest country in terms of that cashless society. The U.S. been talking about for many years how to transition into a cashless society, but China is really the one that has achieved that, very significant scale. So last 30 years, it was more of the digitization, called 1.0, 2.0, and now we enter the new wave of digitization, what I call 3.0. And we extrapolate all these capabilities to the physical world, to the biological world. And if you look at all the cars, the trucks, the vehicles, the trains, and everything becoming digital through advanced sensors. And the roads, the traffic lights of the cities are becoming digital. And the electrical grid and the machines, factories becoming digital. Our home become digital, all the gadgets become digital. So that is so profound and significant. And if you look at the data generates from this, it's just enormous. It's orders of magnitude higher than what we had in the digitization of 1.0 and 2.0. Just take a car, for example. Autonomous driving car will collect somewhere between 2 and 3 terabytes data per day. Just imagine that scale. And in the same time, this trend taking place in the biological world. Our brains becoming digital, our organs becoming digital, our bodies, our genomics, all this becoming digital through advanced this miniature neuron sensors and the bioelectron chips. And again, the data here is even more unmanageable, let me use that word, than what we had in the 1.0, 2.0. So taking the human genomics as example, and each HTS generates just about 3 terabytes per person per sequencing. Okay, you have 3 billion those base pairs, and each with 4 different symbols. For those of you familiar with our genomics, so that data, the whole data is simply astronomical, and that is quite significant. In fact, it drives some of the growth in the artificial intelligence. And we spend a lot of time today talk about AI, and AI is actually not that new. It's been around for over 60 years, and up and down with the different type of technologies, approaches, and algorithms. Initially, it was more of the logical reasoning, trying to mimic a human brain. That didn't work really well. And then there was the expert system, based on really the database, all the experts. It's data driven, but it's more of a narrow domain, expert system. And then it's really in the last 10 years, especially last 5 years, a new set of technology called machine learning and deep learning started to take a stage. And that really took a lot of the center stage that became a mainstream of AI as we know today. And then indeed, in the last decade, the progress on deep learning is staggering. In fact, I was super impressed with what we achieved today. And if you look at the perception level, and the machine learning is able to achieve almost the same level as human being, whether it's speech recognition, face recognition, and object recognition. And then cognitive level, in terms of understanding the language, understanding the knowledges, the video semantics, the machine translation, there's still some distance. In fact, I personally think the current deep learning approach will not be able to do this at the same level, achieve the same level as human being. It requires a breakthrough, requires some fundamental breakthrough in terms of our approach. And indeed, a lot of the deep learning and it's based on a large amount of data. It's based on a lot of training, a lot of parameters, and we talk about reinforcement learning, representation learning, transfer learning, and the RNN, the CNN. In the last few years, the GAN and the BERT are becoming quite interesting. I'm not going to decipher those words. For those of you who are familiar or have an interest, please look them up. And if you look at BERT, the most recent technology or recent version coming out of OpenAI, called GPT-3, has over 100 trillion, right? Over 100 billion parameters. So that kind of scale and magnitude, it's just very hard to keep so for the future growth. So that actually call for innovations and a breakthrough in terms of our architecture, whether it's computing or communications. And if you look at in the AI industry or IT industry, in the last 50 or 60 years, there are a lot of theories, a lot of models, so architectures and laws. But I consider 3 of them among the most relevant, most important ones. And the Shannon's law, and you some of you probably heard of Cloud Shannon, and he's one of the most respected giants. I personally had a lot of attachment with since I started my career with image and video compression, and his theory on entropy and the distortion theory was really the basis for all the work I did. So entropy, of course, is the lower limit of information representation. In fact, he invented the word bits, right? The bit as we know today. A channel capacity is the upper bound, it's the maximal amount of information we can transmit over a particular channel with, of course, in presence of noise. And that limit, whether in terms of the source and the entropy, or in terms of the channel capacity, are being approached. Right? If you look at the most recent MPEG and H.266, and it's really close to the redistortion bound that Shannon has defined. And the 5G communication and the polar code, the turbo coding, that has kind of very close to the limit of the channel capacity. So in the future, we need to have a fundamental breakthrough, in terms of how we actually transmit more information and achieve more compression. The second, I call it architecture, is really the Van Neumann architecture. That has been around for 60 years and is still define the mainstream of our computing model. So his model was actually quite simple. 5 basic components of a computer system architecture. There's instruction, programs, data, all treated as a binary sequence, put into memory and executed sequentially. And that was a beautiful invention, and it's simple, it's so well understood, well optimized. But there's a bottleneck, because of everything is putting together, and you will have issues with the limitation. CPUs and data are competing for resources. They're multi-core, they're multi-CPU pipeline. All the technologies try to remove that bottleneck, but obviously, fundamentally, there is a structural limitation. There's a second limitation. The third limitation is Moore's law. You heard a lot about Moore's law. Moore's law is not exactly a theoretical, a technical law. It is more of a empirical and industry law. So it really says, by putting a lot of investment, a lot of our IQ, innovation, the density of semiconductors will double every 18 months to 2 years. That has slowed down, and in a few years, it might achieve some limits. So we need to remove that limit. We need to have a breakthrough in that as well. So indeed, in the last few years and going forward, we do see new innovations in terms of our system architecture for computing, and also communication infrastructure in terms of how we actually deliver, how we communicate our computing and our bits. So we see a lot of activities in new silicon, this new stack, from the CPU to GPU to FPGA. Those are the accelerators, and now to ASIC specific, ICs that's optimized for AI workload. Bear in mind, I just told you, there's a lot of data, there's a lot of computation, and just a traditional CPU, even with GPU, FPGA, are really not optimized for AI, and we need AI specific optimized workloads. So that really requires also new data flow model, new computing and algorithmic architecture, because AI, if you look at machine learning, all the algorithms I was talking about, it really has a very different type of requirement. It requires a massive data parallelism. It requires differential gradient optimization, linear algebra, the Boolean functions, and also high bandwidth hierarchical memory. Those are very different from the traditional Neumann model as we use today. We also need new sensors for new applications, the LiDAR, cameras, ultrasound, structure sensors, 3D sensors. Those things, again, connect the physical world, the biological world with the information world. So there's a tremendous innovation in that space. And obviously companies like NVIDIA, Intel, AMD, Xilinx are super active. But also you see companies like Google and Baidu, the company have a huge workloads, are beginning to produce own chips, TPUs from Google, Kunlun from Baidu, because those companies own just a huge amount of frameworks, their own models, and of course the workloads. So they know the best how to optimize the workloads with a end-to-end stack and architecture. We also see Chinese startups begin to do a super impressive work. Obviously, Capricorn Han Wuji, you heard about, just went to IPO. And also a company called Horizon Robotics. And I talked with the CEO of the company, Yu Kai, just last week. And the chip they produce, Journey 10, that's the one they're going to produce end of the year, is probably the best in the industry for autonomous cars, and rival the very best from Tesla, from Mobileye, that's part of Intel right now. Just a tremendous development, advance in the Chinese the chip industry, the AI, application domains. In the same time, the 5Gs. And actually, for the first time, it's pushing the intelligence into edge. And I'm not going to spend a lot of time in the communication part, but this is also significant. And I remember in the early days, everything was centralized, right? The mainframe computer. And then in the PC days, then everything become distributed. And then in the cloud computing days, we're trying to have a lot of our capability, computation, storage, and training, concentrated on the cloud. And right now we see a more balanced architecture is probably more distributed. That a lot of this data, computation, intelligence, inference, or even training pushing into the very edge. I would say in the next 5 years, over 90% of the computation happen right on the edge, the device itself, not in the cloud. That is significant because just too much data, we can't transmit. There's no need to transmit. It just there's a latency issue. It just deal that at right where it happens. So that kind of technology advancement in terms of the new digitization, in terms of the new algorithms, and also in terms of the architectural and the infrastructure breakthrough are the foundation for some of the new development in the industry. You heard the word, the fourth industry revolution. AI is the foundation, the technology foundation for a lot of the industries in the fourth industrial revolution. And obviously, it elevates the IT industry, and more data, more computation, more silicon, and more application, more products, more software, and bigger industry. So that itself it's continue to be elevated. AI is changing every aspect of the existing industry. Sometimes it actually disrupts a conventional industry, financial and education, medicine, and healthcare, retail, and communication. Every single industry will be changed, bigger or small, by the innovation I just talked about. It's also going to create new categories. lots of new products and industries will be created by this revolution. And I just list the three, because those are the ones I personally have a lot of passion and attachment. And the first is driverless cars, autonomous driving. The second is industry AI or industry IoT. That itself is a direct extrapolation, extension of our consumer internet. And also the transformation in the healthcare and advanced medicine by AI. I won't have time to talk about all of those. Let me just pick one. The first one, to just talk a little bit for maybe 10 minutes, and I'm happy to answer questions after that. So automotive is actually a very, very old industry. It's been around for 100 years. And in the industry landscape, the supply chain, all the industry is quite mature, quite stable, well-defined, well-developed. You have companies who produce cars, who sell cars, produce all the parts, and also do all the operations. But in the next 100 years, well, let's just say next 10 years, it's going through a fundamental transformation. And the auto industry, we call it the case. It's connected. And if car is becoming a mobile device, and all the capabilities, informatics, the telematics, all the internet capabilities are in the cars. Electrification, that the car will be driven by batteries, not by the gas. And that has fundamental implication on cars, because lots of the innovation in the past was based on engines. In the future, you don't have engine anymore. It's just circuits. It's batteries of circuitry. And the sharing economy, you see Uber, you see in the Didi, whether Gojek or Grab Taxi, happening all over the world. But the most significant, or the interesting, or the exciting, the one that has a lot of frenzy and hype, imagination is autonomous driving, is to apply an AI to cars. So what is autonomous driving? And according to the definition of the Society of Automotive Engineers, it has 6 different levels. The first level, level 0, has no automation. Those cars probably don't exist today. And the highest is, of course, the full automation, level 5. You can drive cars anywhere, any condition. Okay, essentially there's no driver. The car drives itself. And level 4 is the same thing, but has certain constraints. Really the difference is that you have a driver, you drive the car, or the car drives you. Those are the key differences. And the one I talk about the most is the one that you don't need to drive. The car will drive you anywhere, anytime you want. And also, driverless cars, autonomous driving, it's been around for a long time. This is one of those human and dreams, imagination. It's been around for 5,000 years. That's what I heard. In fact, go back to Huangdi time, 5,000 years. I only see a cartoon. I didn't see a car. It's the vehicle. It's just trying to use the magnetic field of Earth, and of course, it points to the south automatically. And I was told, I read some books, that this concept, this notion of autonomous vehicle was actually built in the Three Kingdom days, 1,700 years ago, and also used for sending in the goods. So essentially, it's the precursor to today's logistic delivery. Anyway, those are was quite interesting, but the most exciting development happened in the last decade, especially in the last 5 years. People always ask me why we are doing this. by companies like Google, or especially Baidu. I was the president of Baidu for 5 years. I spent a lot of time and getting into this field. Why are you guys doing this? So there's three reasons. And the first and the most significant reason is safety. Okay? Is safety. And if you look, over 1.2 million people are killed every year by car accidents, and over 90% of those are human errors. People get sleepy, they get drunk, they read their Facebook or WeChat, and they get distracted. They get into accidents. And machine AI can avoid that. So you talk about a safer, more reliable car that save lives, and so orders of magnitude safer. And efficiency. Obviously, when car drive you can enjoy, you can do whatever you like, and save a lot of time. And according to a recent study, you save at least 50 minutes a day. And some people like to drive. A lot of people don't like parking, right? So I haven't heard a single person enjoy parking or find a parking garage. And actually 35 minutes of your 50 minutes is in trying to find a parking space. So with that saving, your life becomes better, city becomes cleaner because you reduce the carbon emission, and also you reduce the congestion. So it's really the societal efficiency, societal benefits. And obviously there's enormous economic benefits, business opportunity. And a recent study, we in Baidu did with McKinsey, was that in the next 10 years, right, and the whole new technology going to generate a business or economy over $1.5 trillion a year. So that is about the robot taxi, about all the services, data service, technology service, cloud service, and autonomous driving technology, all the service associated with this new technology. 1.5 trillion is a lot of money. Okay, just give you a comparison. This is bigger than the entire IT industry we know today. Right? The whole information technology, software, hardware, Microsoft, Intel, Google, all the Amazon, all the big companies today, it's 1.3 trillion globally, including China. Globally, 1. So this is bigger than the entire IT industry. So that is hugely exciting. Then people always ask me, "Wow, this is exciting, but it's gonna really working? It's gonna work, or when it's gonna work? Or when we're gonna see those cars?" Before we talk about that, let's look at how people drive. Essentially, machine is trying to mimic how we drive. Driving is, I think a lot of you know how to drive. Some of you are learning how to drive. Actually, my son is just learning. He got his license. He's learning about driving. So driving actually is quite complex. If you look at our brain activities, right, it involves all the three parts, three layers of the brain. Using the Paul MacLean's simple model, the primitive, the limbic, and the neocortex. The neocortex is a little more, it's the one that has all the logical reasoning, decision, and consciousness. So that is kind of close to our external part of our brain. So it uses all those parts, and also it uses the scientist actually, Eric Kendall, a Columbia professor, is a Nobel laureate, and he developed a lot of the theories in memory. and they call it the explicit and the non-explicit memory and decision making. A lot of our driving are explicit when we learn how to drive. You look at the traffic lights, you look at the signs, you look at other cars, and you make a decision. Should I accelerate? Should I change lanes? But once you're familiar with that, you drive well. You don't think about it anymore. It becomes non-explicit. It becomes a reflex. It becomes that memory. But if you go to a new city, you're trying to find a parking lot, and then that there's a conversion from non-explicit to explicit. And also similar concept, because System 1, System 2. If you read the book Thinking Fast and Slow by Daniel Kahneman, is also a Nobel laureate. And you have not read those books, please do. It's hugely enlightening and interesting. And those two things actually are slightly different. They look at things from different domains. Eric Kendall, and I had a wonderful discussion with him just last summer. I mean, he really looked at this from a neuroscience point of view. And Daniel Kahneman looking at this from more of a behavior science point of view. So, but System 1 is the one that you do not think, right? It's more of based on instincts. It's thinking really fast if there's any thinking. The System 2 is more of the logical reasoning. It's you make decision based on data and that more of a conscious decision. So driving involves all of this. It is quite complex, and it's amazing. We actually can do that in a relatively safe way. Now let's look at machine. So machine has to do all this, perception. You have to see all this stuff. Cognition. You have to think. Have to make decision, and especially you have to use the sensor motor function, because this happens in a highly mobile, moving environment. So you have to take action, and you have to do that real time, flawlessly, hopefully, and responsibly. That's what I tell my son. You have to remember the three things, and carefully, of course. So for machine to do that, it requires accumulation of a lot of critical technologies. They all have to work. They have to work together. Perception and the planning, the prediction, the simulation, the high definition, the mapping, and localization. You have to know where your car are precisely to the precision of centimeters, not meters, centimeters. And you need a lot of software, a lot of and hardware computation on the board. You need the connectivity and all the stuff, and of course the safety, system safety, and functional safety, and the security as well. So it is very complex, but it's achievable. It is complex, it's hard, but it's something that people do. And for a lot of smart kids, they have trouble driving. And for people who never go to school, they can drive well. So it is relatively independent of the education level, but it is complex. Right? So in that sense, I will conjecture that it is probably the most difficult narrow AI problem. It is not a general AI problem. It's a narrow AI problem in the sense that it can be decomposed into tasks that are well-defined, that have a closed form solution, and are abundant. So in a sense, it can be solved. It is not an unsolvable issue. So driving without people or car that drive itself is achievable mission. It's hard, but it's achievable. Okay, I'd be happy to talk more about this because this is just my personal view, and actually I form a lot of the basis of my personal investment, my personal and research and a lot of the big projects we've been driving, and also the things I will continue to do at Tsinghua University. Then people ask me, when this is going to happen. And indeed, in the last few years, there's a lot of investment activity, a lot of media hypes. Some are real, some are not. And the money that the VCs and the PEs put into space are huge, right? Both in US and China. It is, in fact, the largest investment segment. If you look at AI vertical in US and China, worldwide. And so a lot of trials, a lot of innovation activities. But also there are hurdles, there are doubts, there are uncertainties. We see accidents from Uber. We see Waymo, as a Google autonomous driving company, and the Cruise, that is a GM unit for autonomous driving. They all kind of push out and delay their commercial deployment. And a lot of companies think they're going to have all those cars driving in the street this year or next year. Yeah, well, that will probably be delayed a little bit. We also see Tesla, having the autopilot mode running into accidents. So, there obviously there are issues, there are challenges, there are difficulties, and there are a lot of issues, decisions to be made to make that realistic. There are market forces, there are non-market forces. Market forces are the ones that, I think we can control. The technology feasibility, user demand, business models, roadmap, the ecosystem. Those things, somehow are manageable, are predictable. There are also non-market forces, the government policies, the regulations, ethics, privacy, all the other things which we might not be able to control. And obviously, I'm not going to talk about all of this for lack of time, but let me just give you a chart to tell you what we believe when this is going to happen. There are people who are super optimistic, like Elon Musk. He thinks Tesla is going to achieve level 5 autonomy by the end of the year with that autopilot FSD. I think I like him a lot. He's a great guy, but he's probably a little bit over optimistic. There are also people who are very pessimistic. They think this never going to happen. And the truth is somewhere in between. And I'm not going to go through this chart, but what this says, in 10 years, you're going to see probably 15% of the new cars are some level of level 4 or level 5. So that is really significant. It might push this out in or out for 5 years, but I think it will happen in mainstream in that time frame. And indeed, you see a lot of level 4, level 5, maybe level 4 already being used in the vertical domain, and whether it's for cleaning, for agriculture, for logistic delivery, and it's already happening. And especially in the COVID-19 crisis, this has been used in a lot of hospitals for deliver medical necessities and food as well. So let me just spend the last 2 minutes talk about the new institute I'm preparing, I'm incubating. It's called the Institute for AI Industry Research, AIR, at Tsinghua University. And it's, I don't need to convince you why I do this in the things I talk about just now. It is really the very rationale and the backdrop, why I'm continue to be excited about the AI transformation in the whole industry. So the vision for AIR is very clear. We want to advance the humanity, society, and the industry with innovation AI. The goal is to create a leading global R&D center on the fourth industry revolution. And to do this, we need to first hire the very best, like you, the best and brightest from around the world. And we have to create, of course, the foundational technologies. And we want to become an engine for the AI industry and the startups for China and for and globally. The research, very simple. I picked the 3 things I feel most passionate about: AI for transportation, AI, IoT, and AI for healthcare. Those are also the areas Tsinghua University have a lot of strength. Tsinghua has a super strong computer science program, has a super strong electrical engineering program, life science, and also has a top school on the vehicle and the mobility. All this innovation requires a close collaboration with all those disciplines, all those schools, departments. That's the reason I like to set up this institute at Tsinghua University, because I had the option to do this anywhere, a lot of places, and Tsinghua is just the perfect place to do this. To do this, we need, of course, in the top scientists, and I'm glad to have Dr. Zhao Feng and Dr. Ma Wenying join me to co-start this center. 2 of them are just world-leading academics and also technologists. Dr. Zhao Feng was the CTO of a company called Haier, and he was a former Stanford professor, and he was also my deputy back in Microsoft Research Asia. Dr. Ma Wenying is very similar, and his VP and the head of AI lab of a company called ByteDance, 今日头条. He was also my deputy, was the deputy managing director of Microsoft Research Asia. He's one of the world's most prolific and highly cited computer scientists, probably top 10 in the world. A lot of papers, a lot of citation, H index 120. So with that, I will close my talk. And again, we're hiring. We're hiring the best and the brightest experienced professors, researchers, postdocs, and also the young, the potential smart folks like you. Send your resume and to us. I'd love to be part of this whole journey, and I thank you for that.